A production line that can build a vehicle in under 30 seconds, a machine the size of a house, and a plan to eliminate nearly 1,000 welding robots from a single factory. That's not a concept from a science fiction film. That's what's currently being assembled at Tesla's Texas facility. But here's the part that almost nobody saw coming. The most radical shift isn't in the machine itself. It's in the question that started everything. How big can a casting machine actually get before it hits the limits of physics? That question wasn't rhetorical. It was an engineering directive. And Tesla has spent years trying to answer it in metal, pressure, and molten aluminum. To understand where this is headed, you have to go back to where it started. The first generation of Tesla's Giga press machines gave the company something no major automaker had done at scale before: the ability to replace dozens of individually stamped and welded parts with a single large aluminum casting, instead of assembling a rear body section from a patchwork of smaller components stitched together by robots. A single machine could produce it in one shot. That was already a significant shift, but Tesla didn't stop there, as clamping force increased across successive generations, from the machines used on the Model Y to the next round of development. Each step pushed the boundaries of what was structurally possible in a single cycle. Now Tesla is targeting a fourth-generation Giga press with up to 50,000 tons of clamping force. That figure is so large it's easy to dismiss as marketing. It isn't. Here's what that number actually means. The clamping force in a die casting machine isn't the force used to shape the metal. It's the force used to hold the two halves of the mold together while molten aluminum is injected inside at extreme pressure. When liquid metal enters the mold cavity, it pushes outward in every direction. The larger the mold, the greater the surface area, and the greater the force trying to split the mold apart at the seam. If the clamping force isn't sufficient, the mold separates at the worst possible moment, ruining the casting and potentially sending molten metal where it shouldn't go. So when Tesla talks about 50,000 tons, it's not describing a bigger hammer. It's describing a machine capable of holding together a mold large enough to produce something that has never been cast in a single cycle before. And speed is just as central to this as size. According to Elon Musk, the goal is to push casting cycle times closer to what you'd expect from an electronics assembly line, with each cycle taking around 5 seconds and multiple components potentially produced within a single run. To hit that target, the entire process has to be engineered down to the second. It starts with this aluminum, raw material and recycled aluminum from previous cycles, are fed into a furnace and heated to around 850 degrees Celsius until fully molten. Surface impurities are removed, and the liquid metal is transferred into a sealed holding furnace that keeps it at a precise temperature, ready for the next injection cycle. Technical documentation describes a two-furnace setup, one for melting, one for holding, which allows the system to maintain a continuous supply of properly conditioned metal without interruption. But molten aluminum isn't passive. It reacts with its environment and can trap gases or pick up unwanted particles during the process. To address this, the system uses a controlled gas environment, argon degassing, and silicon carbide filters to bring the metal to the required purity level before it ever touches the mold. Once the metal is ready, the mold itself is prepared. A thin layer of lubricant is applied to every surface to ensure clean part removal. Then a vacuum is drawn inside the mold cavity to eliminate trapped air. Because at this scale and speed, even a small pocket of gas inside the casting can compromise the structural integrity of the finished part. Then the piston fires. Molten aluminum is driven into the mold cavity at enormous force, and from that point forward, everything happens within seconds. The margin for error is nearly zero. Inject the metal too fast and trapped air or turbulence creates internal defects. Inject it too slowly and the aluminum begins to solidify before the mold is fully filled. With a component this large, a single section that fails to fill correctly turns the entire part into scrap. Once the casting is complete, the part is removed from the mold at temperatures that can still be close to 400 degrees Celsius. It passes through a cooling system to bring the temperature down rapidly. The mold itself is simultaneously cooled, cleaned and prepped for the next cycle. According to technical documentation, this entire sequence is synchronized tightly enough that the next casting cycle can begin within 1 to 2 minutes of the previous one. Trimmed excess aluminum is fed directly back into the melting furnace, keeping material waste to a minimum, and every finished component is inspected using X-ray imaging to catch internal defects that would be completely invisible from the outside. Now, why does any of this matter beyond the factory floor? Because every part you eliminate from a vehicle eliminates an entire chain of downstream work. A traditional vehicle body is assembled from hundreds of individual components, stamped, welded, bolted, riveted and bonded together in sequence. Every joint is a manufacturing step, every step requires equipment, every piece of equipment requires floor space, maintenance, calibration, and quality control. Tesla's strategy is to compress that entire chain by replacing clusters of smaller components with single large castings. According to available documentation, Tesla has been targeting roughly 80 major structural components for the Cybercab, compared to around 200 for the Model Y. If that holds in actual production, it represents a fundamental change in how a vehicle is architecturally conceived, not just how it's built. There's a common concern that comes up at this point. If a structure is made from dozens of welded pieces, you can replace a damaged section. But if those same pieces are consolidated into one massive casting, does any damage mean replacing the entire thing? It's a fair question, but the answer depends on how the casting is designed to be repaired, not simply on the fact that it's a single piece. Tesla now provides specific repair procedures for the Model Y's rear mega casting. Technicians can cold straighten bent sections, weld small cracks, apply reinforcement plates, and replace individual rail sections without touching the rest of the casting. Full casting replacement is only required when damage affects structurally critical zones or exceeds defined thresholds. In 2025, Thatcham Research, an organization specializing in automotive repair and safety, published findings from 2 years of crash testing and repair work conducted directly on the Tesla Model Y. Their conclusion was that the mega casting was not only repairable, but in the cases they tested, it could actually cost less to repair than a comparable traditional multi-piece steel structure. Repairing a damaged section of the Model Y casting came out significantly cheaper than the equivalent repair on the Model 3's conventional rear structure. Even full casting replacement came in at a lower cost than many expected. The concern about repairability was never unfounded, but real-world testing has shown that the outcome depends on design intent, and Tesla has put measurable effort into making the casting repairable. This brings us back to the Cybercab and why the 50,000-ton Giga press is being developed specifically around it. At first glance, the pairing seems backwards. The Cybercab is smaller than the Model Y, so why would it need a dramatically larger machine? Because Tesla isn't trying to cast a bigger vehicle. It's trying to cast more of the vehicle in a single cycle. With the Giga press currently used for the Model Y, Tesla can produce the rear body as one large structural casting and the front body as another. But those two sections are still joined in a separate process, meaning the body still requires additional assembly steps to connect them. The 50,000-ton machine, if it reaches its design targets, would allow Tesla to produce the entire Cybercab body structure in a single casting cycle, front, rear, and the structure connecting them, all in one shot. That's why the clamping force has to increase so dramatically, even though the vehicle is smaller. Casting more of the structure at once means a larger mold, more molten aluminum injected simultaneously, and far greater forces acting to separate the mold halves. The size of the machine is driven by the ambition of the cycle, not the size of the vehicle. If this becomes operational at scale, Tesla could continue removing robots, eliminating joints, and cutting assembly steps, while reducing the time it takes to produce each vehicle body to something that will would have seemed impossible just a few years ago. Elon Musk has stated that the 50,000-ton Giga press could potentially cast 5 vehicle bodies in a single cycle, and has suggested the Cybercab could reach production volumes exceeding those of the Model 3 and Model Y combined. And there's one more development worth watching. Tesla is exploring the possibility of integrating color directly into the material of the body panels, bypassing the conventional multi-layer paint process entirely. If that works at scale, it wouldn't just mean a faster casting line. It could mean eliminating the paint shop altogether, which is one of the largest, most energy-intensive, and most capital-heavy parts of any automotive factory. That story is still developing, and we'll cover it in a future episode. What Elon Musk asked wasn't really about the machine, it was about the vehicle. How much of a car can a single casting produce? Tesla is in the process of finding out, and the answer may force every other automaker to rethink not just how they build vehicles, but how they design them in the first place. If you found this breakdown useful, hit the like button and subscribe so you don't miss what comes next. Drop a comment below. What do you think is the biggest obstacle standing between this technology and full-scale production?